Hello everyone, I'm Karthikeya Mishra and I'm back with yet another video on data science and business analytics. This video is a full implementation of Gaussian mixture models in Python. We are going to use unsupervised learning of Gaussian mixture models to make prediction. It is an algorithm for clustering and its purpose is to determine the inner structure of data when no other information is available. Let's first import the libraries we are going to be using throughout the exercise. These are some of the most often used libraries while working on data science and machine learning. So please take a look into them. For the purpose of this exercise, we'll be using the iris dataset, which is probably already familiar to you. We can easily obtain it by using the load iris function provided by sklearn. Now let's check the size of the dataset. Let us now implement the Gaussian density function. I know you can use NumPy function for that, but I believe it is actually interesting to see how things work internally. Our aim is to create a function that implements. You can obtain the function by using this code. And you will get something like this. Let us now move ahead to the initialization step of the Gaussian mixture model. Over here, we are going to use the results of k-mean as an initial value for mu underscore k and set pi underscore k to 1 over the number of clusters and cov underscore k to the identity matrix. Let's see what went wrong here. Moving ahead to the expectation step, we should now calculate gamma underscore nk. We can achieve this by means of the following expression. If the expression to find the gamma underscore nk or any other is not clear, you can always check the video description for better understanding of Gaussian mixture model. And now the last step, maximization step. Let us now implement the maximization step. Since gamma nk is common to the expression for pi k, muk and covk, we can simply define it. And then we can calculate the revised parameters by using the expression given in the code. Guys, note, to calculate the covariance, we define an auxiliary variable diff, diff, that contains the given expression. Let us now determine the log likelihood of the model. The summation has already been calculated in the expectation step function and is available in totals variable. So we can just make use of it. At last, let's work it out. First, we are going to initialize the framework by using the initialize clusters and then perform several expectation maximization steps. In this case, we set the number of iterations of the training procedure to a fixed n epochs number so that we can generate graphs of the log likelihood later if we want. The algorithm is motivated by the observations and proceeds as like initialization of the parameter and evaluating the log likelihood. And then it goes to expectation step, and evaluates the posterior probabilities using the current values. And the maximization step estimates new parameters with the current values. Evaluating the log likelihood with the new parameter estimates. If the log likelihood has changed by less than some small value, we can stop. Otherwise, we can repeat the expectation step. Note guys, EM algorithm is sensitive to initial values of the parameter. So care must be taken in the first step. However, assuming the initial values are valid, one property of the algorithm is that the log likelihood increases at every step. This invariant proves to be useful when debugging the algorithm in practice. Something's wrong. Let's check what it is. I have missed quite a few steps here. Damn the indentations. It always takes time to find the errors. Now that we have fixed the errors, let's move ahead. Giving fixed values for n epochs in n cluster to train the data. And now we are going to create a graph to visualize our clusters as well as a framework for the Gaussian mixture. So what we are going to do here is create ellipses of different scales in order to map to the coordinates of each Gaussian. Guys, don't skip the matrix chapter in your school or college, especially the part where they teach you about eigenvalues and vectors. I did that mistake and I had to learn it again from the go. Now let's give the expressions for covariance factor. The angle of the ellipse is determined by the covariance of the data, and we adjust the value of the covariance to see the data is correlated or uncorrelated, which results in an axis aligned error ellipse. So it should be clear that the magnitudes of the ellipse axis, depend on the variance of the data. And our data is a multivariate Gaussian. This means that both the x values and y values are normally distributed too. Let's use the matplotlib function to plot the graph, or animation. Error. And it's fixed. We can now view the error ellipse, also known as confidence ellipse, and the animation of how the cluster estimation improve as time passes. I forgot to verify the log likelihood data. So I'm creating a graph to check the values. I'm going to give the title log likelihood. Now let's see the graph. The likelihood graph shows us the probability of observed data under the model. And let's now test if our calculations are correct. We are going to use sklearn's GMM implementations to check for the parameters and probabilities. I'm going to print means and scores by sklearn and our implementation to compare them. I'm sure no one likes errors. And we are done. You can compare the means by sklearn and our Gaussian mixture implementation. Guys, you can get the code from the GitHub link in the description along with the data. Thank you so much for watching the video.